Hi folks, welcome back to Physics with Captain Rod. I'm making this one to help you out with number 18 in your Unit 4 homework. So let's see, we've got this bar thingamabob, okay, connected by a hinge, free to rotate. And it starts here at position 1, what I'll call position 1, released from rest, and it falls over. So what that means basically is, a moment later it looks something like this, and then a moment later something like this. And then eventually, right before it hits the ground, it looks something like this. All right, that's just kind of a quick sketch. And let's see, what is it we are tasked to find? There we go. Let's see, find the angular speed just before it hits the ground. So hopefully this problem kind of reminds you of something. Right? This is a potential energy to kinetic energy situation. So I would call this position 1. And position 2 is just before it hits the ground. Again, not after it hits the ground. And the object has an angular velocity at position 2. It is rotating. Right? So I would write out the work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. Right? If we put a datum at this level, the PE2 would be 0. Now let's talk about the PE1. So this bar is 2 meters high, right? But the bar is 2 kilograms, and that 2 kilograms is not all at 2 meters. So you measure potential energy from the center of mass of the system. The center of mass of a bar is at its geometric center. So this is the height that you're going to use for the PE1 term. Okay. Now, position 2. The bar is now at the datum. That should give you an idea of what to put for PE2. Now for KE2, the kinetic energy can be expressed in terms of the rotation of the object, 1/2 I omega squared, right? Where again, omega is the rate of rotation. Change in theta over change in time, or in the language of calculus, d theta dt. That's not important for working this problem out. The moment of inertia. Okay, you're going to look that up. This is a bar or a beam with an axis through one end. I'll let you find that. Now, the work term. The work term is again 0, and I try to make a big deal about this whenever I can. Let me draw force vectors, and so that they stick out, I'll draw them in red. And let's look at like an in-between force vector, like at this location, like right here. Right, the gravitational force is straight down, equal to mg. Now, as far as this region is concerned, that's the only force acting. There is a force acting at the pin, and the direction is not perfectly clear. All right, so typically when forces are not known, we usually put them in component form. So I'm going to go ahead and put a px and a py. So those would be like the x and y components of the reaction at the pin. Right? And that's it for the free body. There's nothing else. Now let's chat about work terms. This force is doing work because overall between position 1 and position 2, the center of mass went from this height to this height. So there was a change in this direction. So that thing does do work. But as I point out over and over and over, that's what the potential energy takes into account for you. And notice that if you did do a work term, it would be the force mg times the height h. And that should be what you have under the PE1 term, right? So that's already taken into account. Now let's talk about what's happening here. Those forces, the px and the py, they are external forces. But there is no work done because the pin is not moving. Right? If the pin were somehow moving in this problem, you would need to include a work term, right? But it's not, so you don't. All right. Anyway, long story short, get the work energy written out pretty nicely. That should be able to allow you to calculate the final angular speed, the omega 2, without too much trouble. Oh, and there is no part B to this. Okay, so I guess we'll just call that done. So I hope that that helps. Have a great day.